So now that we have finished the review of probability in 1.3, we can move on and start actually getting back into the meat of quantum mechanics itself, starting with 1.4, which is directly related to the concepts that we went over in 1.3. Let's just consider a wave function psi, and we know that it's dependent on space and time just from looking at the Schrodinger equation. And we know two things about psi. We know two fundamental rules that psi has to obey. The first one is that psi must obey the Schrodinger equation. That is how we actually obtain this value. So psi must obey the Schrodinger equation, which I will just call SE. And the Schrodinger equation is I times h hat, or h bar, times the partial of psi with respect to time is equal to the negative of h bar squared divided by 2m multiplied by the partial squared of psi, or the second partial of psi with respect to x, plus the potential of our system V multiplied by psi once again. So this is our first condition for psi. Our second condition is that psi mag squared is a probability density, where psi mag squared is the magnitude of psi of x comma t squared. And this is directly equivalent to a probability density rho of x dx for any continuous probability distribution. So this second condition sort of implies an extra third condition, which let's just call 2b, 2b, which is all probability densities must integrate to 1. And what I mean by that is, if you have a density rho of x dx, then the integral from negative infinity to infinity of our probability density must equal 1. And this is something that we actually saw firsthand when we did problem 3.3 involving the Gaussian distribution, where we had to actually define the constant a in front of our Gaussian so that the integral did in fact become 1. Now, this kind of puts a lot more restrictions onto psi compared to just the fact that it has to be defined using the Schrodinger equation, because there are a lot of different possible psi values which do obey the Schrodinger equation but don't actually integrate to 1 when you take the integral of the mag squared. And to sort of prove this, psi does not always integrate to 1. Let's consider a psi. Let's consider a psi, and let's denote this as psi naught. And let's say that psi naught does obey the SE, and its mag squared value does integrate to 1. So what I'm saying is that we can plug psi naught into our Schrodinger equation, and it will indeed give us a valid solution. And what we are also saying is that we can plug psi, so negative infinity to infinity of the magnitude of psi naught squared dx does indeed equal 1. Okay, now let's define a new wave function. Let's call it chi. Let's say that chi, that's a bad chi. Let's say that chi is equal to some constant. Let's say that it's equal to some constant c times psi naught. So our first question is, does our new wave function obey the Schrodinger equation? And it in fact does, and we can see that if I just copy and paste this thing down on this side, we can see that if we take the partial of chi, well, the partial of, let's write this in a different color, let's say we can take the partial of chi with respect to time, and since c is just a constant which does not depend on time, it simply comes out, and this actually equals c times partial psi naught with respect to time. And the same thing also applies to the second derivative of psi with respect to space. The second derivative of chi with respect to space is once again simply just equal to c times the second partial of psi naught with respect to time, or with respect to position squared. And the reason why, once again, is because c is just an arbitrary constant. It can simply move out of the derivative. And the same thing applies here. V times chi is effectively the same thing as c times v times psi naught. So we have a c attached to each of these three terms. We can cancel out all of c's, and we get, once again, the same Schrodinger equation as when we just worked with psi naught. So evidently, any sort of constant multiplied onto psi naught still remains as a solution to our Schrodinger equation. However, c times psi naught is no longer square. Its square magnitude no longer integrates to 1. If we take the integral from negative infinity to positive infinity of chi, or magnitude of chi squared, dx, this actually gives us c, because what this actually, or in fact it doesn't, it gives us c squared actually. And this is no longer valid because c, unless c equals 1, this will no longer equal 1, and as a result of that, it is no longer a valid probability density. So the first thing we have to do is we effectively have to throw away any sort of wave function which behaves like this, which behaves kind of like this one over here. These are not, we call these not physically realizable, as in no real life particle can have such a wave function, because the probability density of such a wave function would violate this fundamental rule that it has to integrate to become 1. It doesn't make sense for something to have a probability of over 100% or under 100%. So these are not physically realizable, and we effectively throw all of them away. They are not useful for the purpose of our analysis whatsoever. Now, one thing that we can do is a process known as normalization, which in this process, we effectively take our arbitrary constant c and we say, okay, well, since c times psi naught is always a solution, provided that psi naught is a solution, I will simply always attach a c value in front of any of my given solutions, and I will choose c. I will pick and choose it in such a way so that the wave function does end up integrating to 1. And if you want an explicit example of this being done, go back and look at the Gaussian example from 1.3. I think it's example 3. I think it's problem number 3. It involves finding the probability distribution for a Gaussian function, and in part A of that problem, we explicitly found the constant in front of our function so that the probability density did integrate to 1. Now, one of the problems that arise when we introduce normalization comes from the fact that psi is not just dependent on position x, but is also dependent on t. If we just look at this Schrodinger equation, the fact that there's a partial of psi with respect to t implies that our psi function is a function of both position x and time t. And just because we have some normalization value c, which allows psi to be normalized, or allows its magnitude squared term to integrate over all of space to 1 at some specific time, we don't necessarily know that it will stay that way over all time. And what I'm saying by this is, let's say that we have a normalized function. Let's say that the integral from negative infinity to positive infinity of our constant, let's call it c times psi of x comma t. And let's say that at this point we're defining t to be 0. So x comma 0. We take this magnitude of this and square it, dx. And let's say that this does equal 1. So this is a very nice wave function, and everything works out, and we don't have any problems. Now, the problem comes about when we allow psi to evolve with time. So let's say instead of x comma t equals 0, just x comma t, where some arbitrary time later. This, we do not necessarily know if this is true. We do not necessarily know if our normalization constant c remains as a good normalization constant with respect to time. Now, I could define a new c. I could define a new constant, and instead of c, I can define, let's say, a new constant and call it a, and say that with this new constant at time t, psi does in fact become normalized. However, that sort of violates the assumption that this is a constant, because if c changes with time, it is no longer a constant. It is now a function of time. And if it becomes a function, then psi will no longer obey the Schrodinger equation, because the partial of psi with respect to t will now actually depend on what c actually is. So we are not allowed to just change our normalization value. So evidently, the thing that we require is that c must stay as sort of a good normalization constant over time. So our requirement is that c, the normalization constant c, must remain as a good constant for normalizing psi as it evolves over time. Now, thankfully, this is in fact true. However, the proof for this is a little bit, shall we say, mathematically unintuitive. And unfortunately, because of the fact that this is an introductory textbook, we will run into this problem more and more, where Griffiths will kind of just throw math at us, and kind of we are unfortunately forced to accept it. But that is an unfortunate fact of any sort of complex, full-depth introduction course, is that we are going to be introducing a lot of very weird, wonky mathematics and whatnot that we kind of just have to take at face value. So I unfortunately will have to ask you to sort of take the derivation at face value as well. So let's kind of just get started with this derivation. So our requirement is that the normalization constant c must remain as a good constant over time. So what this tells us is we require that d over dt of the integral from negative infinity to infinity of the magnitude of psi of x comma t squared dx, we require that this equals 1, or 0, in fact. If we wish for our normalization constant c to remain as a good constant over all of time, then the total sort of area that is marked out by our probability density of mag psi squared must not change, because the moment it changes, the square mag of c times psi will no longer integrate to 1. So let's start sort of by moving our d of dt into our integral. So this becomes the integral from negative infinity to infinity of the partial with respect to t of the magnitude of psi squared dx. And I am going to leave out the dependence on x and t, just to make this sort of easier for me to write. So our goal now is to sort of evaluate this function, and we want to prove that this becomes 0. So let's try this. And we will begin with sort of what actually the magnitude squared of psi actually means. So magnitude of psi squared. Now, we know that psi is complex, so the magnitude squared of any complex function is actually equal to the multiplication of its complex conjugate, psi star, multiplied by itself. And this is true for any sort of complex number. If you're not familiar with this, then it might be necessary to sort of read out on that a little bit. We will not go into detail regarding that here, just because that will take too long. But yeah, because psi is complex, since evidently the Schrodinger equation which determines it has complex numbers in it, we will define it in this way. So the partial with respect to time of the magnitude of psi squared therefore equals the partial with respect to time of psi star, which is the complex conjugate, multiplied by psi. From here, we can use product rule, and we can say that this equals the partial of psi star with respect to time times psi plus psi star partial of psi with respect to time. And what I'm doing here is just product rule. So box prime times triangle plus triangle prime times box. The partial, you take the partial of the first one, multiply onto the second one, add it with the second one, multiply by the partial of the first, etc., etc. Now, note that we have partial psi star with respect to time and partial psi with respect to time, and this is kind of where the next step sort of comes out of nowhere. We're going to take our Schrodinger equation and note that we can actually define partial psi with respect to time in terms of the rest of this mess. So we can actually say that partial of psi with respect to time is in fact equal to 1 over I h bar multiplied by negative h hat squared divided by 2m times partial squared psi with respect to x squared plus v times psi. And then the same thing, if we want to attach a star, if we want to do the same thing for the complex conjugate, we can simply attach a star onto psi, attach a star onto psi, attach a star onto psi, but the equation is otherwise effectively identical. And if we do this, allow me to zoom into my canvas a little bit more. If we do this, I will leave sort of the math to you because it is a very tedious calculation. What we will find is that partial of psi with respect to time is equal to I h bar divided by 2m times the partial squared of psi with respect to position squared subtracted by I divided by h bar times the potential of our system v times psi. And what we will find for the complex conjugate is that partial psi star with respect to time is equal to, and remember when we're dealing with complex conjugates, all of the imaginaries get a negative in front, so this becomes negative I h hat over 2m partial squared psi star with respect to x squared plus I over h hat v psi. So for the complex conjugate, I actually, in this case, I might have defined it wrong. There are supposed to be negatives. You have to, if you want to attach a complex conjugate, you have to attach negatives in front of all of the imaginary terms. So for the complex conjugate version, there would be a negative here, and you would have to multiply over with all of that. And if we sort of plug this in to our partial with respect to time of psi squared, which we expanded right here, what it becomes is the partial with respect to time of the magnitude of psi squared ends up equaling I h hat over 2m times psi star times the second partial of psi with respect to position subtracted by the second partial of psi star with respect to position times psi. Apologies for this, but I just realized I made a small mathematical mistake in my work. For this expression defining the partial of psi star with respect to time, I left out the conjugate on the very end term here. So this is actually I divided by h hat, or h bar, times the potential times psi star, not psi. However, this expression is still correct. So we have kind of gotten to this point, and we have this expression. The next thing I'm going to do is not mathematically intuitive. So what we will do is I will claim that this is equal to another expression, and from there I will prove that that expression does in fact equal our original term. So from this point, I'm going to make the following claim. I'm going to claim that this expression is in fact equal to the partial with respect to x of I h hat, or h bar, divided by 2m, this time times psi star times partial times psi with respect to x subtracted by partial psi star with respect to x, this time times psi. And this seems like a bit of a concerning transition, because it seems like I'm just pulling out a partial derivative through distributive property without taking into account product rule. But this does indeed equal this. It is not ignoring product rule. It just so happens that the extra two terms that come from using product rule end up canceling each other out perfectly. And just to make sure that you're okay with this, we're going to do this fully. We're going to expand this fully, and we're going to do the proof in reverse and show that this does in fact equal this expression. So let's just do that right away. I h bar over 2m is a constant, so it doesn't factor in. So we're just going to say that this equals I h bar over 2m multiplied by then d psi star with respect to dx times d psi with respect to dx plus psi star with respect to partial second of psi with respect to x squared, where I'm using product rule on this first term. Now we do the same thing, use product rule on the second term, so subtracted by partial squared psi star with respect to x squared times psi subtracted by partial psi star with respect to x partial psi with respect to x. Now, as we can see, these two terms actually end up canceling each other, and we get this term in the middle here. So this becomes I h bar divided by 2m times psi star partial squared of psi with respect to x squared subtracted by partial squared psi star with respect to x squared multiplied by psi. And indeed, if we compare these two, they are in fact the exact same expression. So our claim is evidently valid, so let us copy this and move it down and we will say that d, well, let's do this in black. Let's say that d over partial of time of our psi squared term, psi mag squared term is equal to this. Okay, so we now have this sort of expression which we have equated to our original expression, but it's still not necessarily clear what exactly we have to do here. So let's kind of go back for a second and look at our original expression. Our original intent was we wanted to prove that the derivative with respect to time of the integral over all of space of the magnitude of psi squared must equal 0, and we moved our d over dt into our integral, and since psi is dependent on x and t, we change it into a partial instead of just a normal derivative. So let's sort of try writing this out in full now. So let's take this, let's move it down here, and we will say, okay, well, if we write this out fully, this is equal to the integral from negative infinity to positive infinity of the partial with respect to x of this entire mess over here. And then we add a dx at the end. Now, hopefully this looks encouraging to you because there is a partial at the front of this entire expression, and this is an integral in terms of x. So what happens is that this actually cancels out. So the partial with respect to x cancels with the integral over x, and what we get is this simply equals the exact same expression. This time we are evaluating from negative infinity to infinity. And our goal now is to prove that this equals 0. So our question is, does this expression in fact equal 0? And the answer to that is yes. And to sort of come to that conclusion, we actually don't have to do any more math at this point. We can simply look at this expression. And what I mean by that is, well, what we want to pay attention to is psi and psi star. So one of the requirements that we made for psi was the following. The probability density must integrate to 1. This is a required property of psi in order for our Schrödinger equation to be physically realizable. Now, what this implies is that this directly implies that psi must go to 0 as x goes to plus minus infinity. And the reason why is because if psi doesn't go to 0 at as x goes to plus minus infinity, the probability density will not integrate to 1. It will integrate to infinity, because if it's approaching some finite number, well, as you integrate, well, the integral is just the area underneath the curve, and if our area is going to some non-zero value as x goes to positive or negative infinity, then our integral will diverge to infinity as a result. So we require that psi goes to 0 as x goes to plus minus infinity, and hopefully you see that that instantly allows us to cross out this right expression, because this right expression has a psi right here, and this term goes to 0 at both positive and negative infinity, so we're instantly allowed to just cross this out and ignore it. Now, the second term, and our focus of interest here is psi star. And psi star, in fact, also goes to 0 as x goes to plus or minus infinity, because psi star, the only thing that changes is that we're adding negatives onto all of the complex terms. However, the fundamental shape of our function still remains the same. If our function looks something like this, for example, then maybe taking our complex conjugate would change the signs around, and maybe it would look something like this instead, where everything would reverse, or maybe part of it would reverse. Maybe instead of that, it would look something like maybe the bottom part reverses, but the top, but the left part reverses, and maybe the right part stays constant, etc., etc. It sort of changes the sign of certain terms, but the overall shape must remain constant. So as a result, we can also claim that psi star, in fact, also goes to 0 as x goes to plus minus infinity. And as a direct result of that, we can therefore also cross out the second term, and as a result, the derivative of our magnitude squared does in fact equal 0. And as we proved up here, this is in fact true. And since the rate at which our sort of periodic density or our probability density is not changing, our normalization constant c sort of remains as a good normalization constant over all of time, and we never have to worry about it not becoming normalized due to time evolution.